So we're examining the impact of Great Lake temperature perturbations on simulated downwind precipitation. So this is part of a project called BREE, which stands for Basin Resilience to Extreme Events. So it's a 5-year project with a grant from the National Science Foundation that was awarded to Vermont EPSCoR, and the purpose of the overland project is to study and promote resiliency in the Lake Champlain Basin. And there's several teams working within that project, and we're working under the climate modeling team with Dr. Cameron here at Linden, and the larger WRF team, which has people based out of UVM and Dartmouth. And the goal of that team is to configure WRF such that we can simulate changes in frequency of extreme rainfall events due to climate change, specifically in the Lake Champlain Basin.
So for our project, we had 3 different nested domains. So the first domain, which is highlighted in blue, that is our first domain, and it's at a 36-kilometer resolution. Currently, we have our ERA interim data that's being fed into the first domain, and our hope is that in the future, we'll have a coarser resolution and be able to put in GCMs for future runs. In green is our second domain, that is at a 12-kilometer resolution, and then domain 3, that's at a 4-kilometer resolution. So the first research question that we had for our project was, what is the most accurate way to represent the Great Lakes temperatures in WRF? So the motivation behind this is that there are various different ways to represent the lake temperatures in WRF. So essentially there's 2 different ways we looked at. There was the default method in WRF, where essentially that takes the temperature from the closest, largest body of water. So what we found was that we are actually getting some of those temperatures from the Great Lakes itself. However, one of our concerns was that there might be some temperatures that are coming from the Hudson Bay and the Atlantic Ocean. And then the second way is the lake update, where essentially it's just taking the temperature from over the lakes. So the methods onto how we were approaching this question was to compare the model values to the observed lake temperatures and then explore some of the pre-processing options.
Okay, so one of the first things that we wanted to do with this is we wanted to just see how these different ways of approximating the lakes compared to actual observations, so which one's more accurate. So this is the WRF default being forced with reanalysis data. So right now we do have some grid cells that are resolved over the lakes, and that's helping to set the temperatures, whereas if we went forward and forced it with the GCM, we would most likely only be getting temperature data from the Hudson Bay for the western part of the Great Lakes and the Atlantic Ocean for Lakes Erie and Ontario. So likely this would be worse. It would be worse compared to observation. Right now, just the way it is, we sort of have somewhat of a cold bias, particularly during the warm season. So we decided that going forward, this isn't going to be a very good method. So we tested out the lake update method, where we're using overlake air temperatures as a proxy for lake surface temperatures. And that method was a lot worse. Particularly in the late springtime, the temperatures of the air were obviously a lot warmer than the water, so that was showing up there. And also particularly in the wintertime, because we were using overlay air temperatures as a proxy, we would result with lake temperatures that were well below 0, and in reality the lakes were pretty much bottoming out at 0 once they freeze over. So that wasn't a good method either. So going forward for the rest of our work, we developed a third way to do this, which was using the sort of a climatology of the lakes, which was basically using the 2010 to 2014 average temperatures for the lakes, but dependent on latitude. So we sort of came up with a different method, and that is plotted here in pink. And so that, it still wasn't completely accurate. There was still, particularly during the summer months, it could be off by as much as 4 degrees Celsius, but it was much better than the lake update method. And so this is just showing some actual values for that. So you can see during the winter time, the lakes, most of them are pretty close to 0, whereas if you look at the middle figure there where we have the lake update model using the overlake air temperatures, all of the lakes are below 0, and in some of the northern parts of Lake Superior, it's almost 10 degrees below 0. And then with the climatology, that sort of fixes that and sets them back closer to 0. Because we also set a lower bound of 0 on the lake climatology as well.
So the second research question that we had for our project is, how sensitive is precipitation in New England to the changing lake temperatures? So So the motivation behind this is that we know that the lake temperatures are increasing and this may cause an increase in evaporation. And actually that was proven. If you can look above in the upper right-hand corner, that is just showing you that evaporation has been increasing over the years. And so why we're concerned about that is that if you look at the 500 geopotential height graph there, you'll see that if you were to be situated at the Great Lakes and say there was some evaporation to occur and then precipitation were to form, then you'll notice that Vermont is actually downwind of the Great Lakes, so we're concerned that maybe this might potentially bring some precipitation to our area that we're not quite used to. So another motivation behind this is that are these temperature adjustments necessary, and then we also want to understand the impact of these observed trends. So in order to go about this question, we had to modify the lake temperatures in the model to examine precipitation changes. So here you're looking at the 2010 and 2014 lake surface temperatures. So in the black line there, that's our lake climatology. And then around it in red and blue are the different lake temperature perturbations that were created from this climatology. So as you can see, we kind of bottomed out at 0 degrees Celsius just because when we were looking at the lake update, we noticed that some of those temperatures were below 0 degrees Celsius. So we're just trying to be as accurate as possible and accurately represent what might actually be happening. So then in the gray there, that is just the range between the maximum and minimum observed temperatures. And as you can see here from this graph, our temperature perturbations exceed our observed temperatures.
So with that, now that we have these perturbed values for the lake climatology that we came up with, and we know that that sort of exceeded the the annual variability during our time period, we wanted to see if there was pretty much right away a correlation between annual precipitation and how warm the lake surface temperatures were. And we found that for most years there actually was a positive correlation like we expected. Some years it was statistically significant, other years it was not. In 2010, 2012, and 2013, those correlations were statistically significant to the 5% confidence level. But what we found is even though we did find these positive correlations between them, the signal or the effect of the lake temperatures wasn't as strong as the variability just on an annual scale. So even though there was an increase here, it didn't exceed that annual variability. So while it was a factor, perhaps it's not the most important factor. So after that, we decided, okay, so on an annual scale, there is some trend, but is there a stronger trend on a monthly or daily scale? So then we plotted, this is daily average precipitation by month. And what we found is some months, pretty much all of our simulations tracked almost identically with each other, but then you have these other months where there was quite a significant spread between all of the different model runs that we did. And sort of our original hypothesis would be that you would always expect the red line, which is the warmer lakes, to be above the blue lines, which what happened a lot of the time, but not necessarily all of the time. And you have certain months like this is August of 2010 where there's quite a bit of a spread. So then we created this graph as a result.
So here we created a one-to-one plot that shows the daily precipitation in domain 3 during 2010 through 2014. And basically what we did was we took the positive lake temperature perturbations and we averaged those, and then took the negative lake temperature perturbations and then averaged those, and then we decided to plot them on this line to see whether or not, if it was actually showing that the precipitation was increasing as temperature did increase. So as you can see on this plot, that the data points were pretty symmetrical along the one-to-one line, but however what you will notice is that there are some cases where you might have more precipitation when the temperature is a negative perturbation versus, there might potentially be, when you have a positive temperature perturbation, the precipitation might also be increased. But there's some cases where the negative perturbation actually had a greater amount of precipitation overall, so this is more of like an event basis from that. So our future work, we'd like to repeat this analysis for other moisture variables. So we'd be looking at things such as dew point, relative humidity, cloud cover, and other precipitation statistics. So essentially, this would be important because if we actually aren't being impacted greatly with precipitation due to this evaporation. This might actually be bringing other things such as cloud cover. We might have more humidity than we usually do. And then another thing we want to do is examine the correlation between the storm tracks and the precipitation in our third domain, and we'd be looking at this in a seasonally basis and then extreme events as well. So with that, we'd like to thank you.
Thanks. You guys are right at 10 minutes. I don't know if you're shooting for anything for time there, but in case you're wondering.
Questions, comments, feedback?
So you showed a lot of graphs there, and I know you guys did lots of great work this summer. One thing that always amazes me when you do science is to get a result that seems intuitive and simple, how much work goes into it. So I'm just kind of curious, not really commenting on your results, more on the process this summer. What was the biggest thing that you guys have learned from what you're doing? Or the biggest headache? Maybe that's another way to ask it. Be brutally honest.
I mean, sometimes the coding was a
Sure.
lot. Like, you'd get hung up on this one little thing. Like, I would have an idea in my head of what I wanted to make, but then there would be one little piece that was preventing it from, like, getting to becoming an actual graph, and that one little thing would stop the code from running, and until you figured that out, it would not work. So that was, I don't know, probably the most frustrating, but then when it worked, it was also very rewarding. So.
I'd have to probably say the same just because I don't really have a lot of coding experience. The only thing that I've used MATLAB for was climate stats. So I mean, I had that background, but it was a little bit over my head at points. And this past couple of weeks, I was trying to, show things on a seasonal level. And I was getting so frustrated just trying to figure out how to, plot it and represent it in a good way. And then I finally got something, and then we noticed that it really didn't show any, statistically significant positive correlations. There was nothing that was amazing out of it. So it was like, oh great, you just stressed out about it for so long and now there's nothing. But I guess that's a part of research and it happens. So
no results are still results.
They are. So
it's not as fun.
Yeah.
That's pretty typical. It's true for all of us when we learn something new. Some of those challenges we face, technically or otherwise. And I think everyone in this room, we all have a lot to learn too. We're trying to learn a new widget or a new software package or this or that. It's just part of learning.
Other questions, comments?
Can you go back to your 1-to-1 graph? There's 3 slides back. Yeah, I'm confused. What is each axis?
Yeah, it needs to be included there.
Okay. So that's just showing the precipitation in millimeters.
So the x-axis.
Right. Okay.
This one's negative, positive.
Oh,
Yeah.
negative is the x-axis and positive is the y.
Yeah.
So that should be put on.
Okay.
Yeah.
Okay.
What were you expecting that plot to look like?
So I think if it would have, I think we were expecting there to be more along, I think, this side. I think because we were looking for the positive simulations to be consistently outperforming, producing more precipitation than the colder simulations, but because we found that sometimes it went either way, we were like, okay, so that's.
Yeah, so the hypothesis was essentially that we should have had more dots up on the top of
Yeah.
that line.
Yeah.
To the left of the 1-to-1.
That makes sense.
Yeah. And it's possible that if we look at it just the right way, that'll happen. but the annual total or annual average is clearly not showing that.
It seems like there's a bit more sensitivity with some of the lesser tools, I could argue.
Yeah.
With some of the what?
With some of the lesser tools, so between 0 and 1 and 10 millimeters.
I actually noticed that too, Francis, when they first put that up. That's why I was wondering which axis was which. Yeah.
So what type of weather systems is the moisture flux from the Great Lakes really going to be the most important? So just thinking about why maybe it's on the 1-to-1 line as opposed to the moisture here coming from the Atlantic instead.
Don't even have an answer.
No, I just
Yeah.
throwing, you guys have done a good
Well,
job.
if you go back,
spewing
go back
things
to
out.
the time series. Yeah, this one.
Yeah.
I mean, there's some months, like if you look at, and we talked about this previously
Yeah,
too, David,
yeah.
but I mean, if you look at the summer in 2010, it
Mm.
looks like there's a pretty strong influence
Mhm.
there, potentially.
Yeah, it's warmer.
And so that was one thing that we want to look at, and we just haven't had time. I mean, these
Sure.
two squeezed basically a 10-week internship into like 6. So
Yeah.
they've gotten a
Yeah.
lot done in that time, but that leaves a lot of unanswered questions. And so one of the things we want to look at is, well, what's going on there? Did we happen to have a lot of storms that, traversed the Great Lakes and came over this way?
Yeah.
What was it about those? So the results aren't necessarily that the lakes don't impact our area, because there is a significant correlation for 3 years. It's just in what way and what's important.
Yeah.
And we still do need to answer this question too, because do you guys want to go back to the one that has the Mallard figures? Lauren didn't really talk about the figure on the right-hand side, but this is really our motivation. You can see that if you look at the continental United States on the left-hand side, on the bottom is the information you get from a GCM. And that's what we're planning on forcing our simulations with, moving in. I mean,
Oh,
if you look at the
just get rid of the Great
2100,
Lakes.
Great Lakes are gone. Yeah, because it's a degree resolution or larger,
Yeah.
and so there's no in the
Yeah.
water bodies. And so one of the ways that WARP handles that during the pre-processing is it takes information once all of a sudden when you do resolve the lakes, it takes information from the nearest bodies of water. So if you look at the right-hand side, the bottom half of the lakes is taking information from the Atlantic Ocean, and the northern half is taking it from the Hudson Bay. And so it's a horrible representation.
Wow.
And so if the lake temperatures are important, we need to figure out a better way to do it. So we still need to answer this question. We still need to try to figure it out. But our team is hoping that we don't care, that it doesn't matter. That's what they're hoping for. We can have terrible lake temperatures and just go with it.
So can we actually go back to the perturbation slide? I think this one, yeah, this one. So this is what you're physically changing the lake temperatures here in the model?
Yeah.
Okay. So basically, the plots you show later on are from these, like, I don't know, 11 different runs that you're making?
Yeah.
Okay.
Did you guys run more? I was
No.
gonna say.
Well, yeah,
I think
the
so.
11
Yeah,
yeah,
doing
11
like
different.
Herculean T, 6 weeks to figure that out. And do that.
They'd still be trying to get a single
Yeah.
simulation off the ground. Yeah.
Were you guys did you help design the deltas there for the range bin? Was that part of your work?
So what we did is we sort of went in and grabbed the data for what actual observation was, and sort of just basically got about sort of showed what the monthly average values for each lake were, and what the average latitude of the lake were, and then Dr. Henry used that information to create this black line here, and then we had a conversation about how we wanted to perturb that, and that's how we came up with these 11 different, yeah.
Good science always leads to more questions, so it's good work.
Any other questions, comments? All right. Thanks.
Thanks, guys.